Going to be over something called the kinetic molecular theory. And kinetic means motion. So this is the theory about how particles move. And so gas particles, we already know from our experience in other science classes, they're really far apart from each other. And then we've added on in our AP class that they really don't have LDFs, dipole, hydrogen bonding, all those forces, because they're so far apart from each other, they don't really have any significant attractive or repulsive forces. The other part of kinetic molecular theory is gases move, they're in constant random motion. They move in straight lines until they collide with another particle or a wall of a container. And we consider these gases to be have elastic collision in which no kinetic energy is lost. There's a kinetic energy equation that is usually more involved in a physics course, but it is a part of this concept, and it's Ke, which is kinetic energy, is equal to 1/2 mv squared. We don't ever actually calculate this equation, but we can use this equation to understand what's going on in a sample of matter. So all particles of a given gas have the same mass. So like if I had hydrogen gas, they all have the same mass. If I had oxygen gas, they all have the same mass because they're the same substance. But they have different velocities, which causes the kinetic energy to be different. And so the main thing that is changing these velocities is how they're absorbing energy from heat. And so when we're measuring temperature of something, we're actually measuring the average kinetic energy of those particles. And so that's the reason if something's at a higher temperature, those particles move faster, they have a higher velocity, their mass is the same, but because they have a higher velocity, they have more kinetic energy. If you have something that's closer to becoming frozen, the velocity is very slow, so they have less kinetic energy. And so when we're talking about the kinetic molecular theory, I want you to think about that equation and just think about that relationship. In your high school level chemistry, you should have studied the combined gas law. This one looks a little bit more involved because it has the P1V1 over N1T1. We normally just do the P1V1 over T1 is equal to P2V2 over T2. But as we've seen in AP Chem, almost everything relates back to how much of a substance we have, so how many moles they have. And so we use this combined gas law a lot of times to predict relationships, to understand what is happening to a situation. And so this one is going to be, this is a sample of carbon monoxide was placed inside a sealed container. We have to look at these words that we use in these things because it's a big deal. So here on this problem, we see that it says that we have a sealed container. And with it being sealed, that means that nothing can come in and nothing can go out, is what it means to be sealed. It says, as the vessel was heated from 100 Kelvin to 300 Kelvin, the pressure remained the same. What changes will occur and why? And you want to consider changes to volume, temperature, moles, and particle speeds. Okay, so temperature increased. That's the information that it specifically tells us. It tells us that our temperature goes from 100 Kelvin to 300 Kelvin. And so the temperature increased. My moles remain the same. And the way that I know that is because it literally said that it was placed inside a sealed container. And that sealed container means that nothing can go into this container, nothing can come out of this container. And then the last thing out of this is that we know that the pressure remained the same. It told us that. It says the pressure remained the same, and so there was no change in pressure. So if our moles stayed the same, our pressure stayed the same, then we can sort of ignore both of those variables out of this problem. And we can just look at the concept of what things could be changing. Temperature is changing. And so in order for temperature to change, that means the other thing had to change would be volume. Now, volume and temperature, since they're both in a direct relationship because it's V1 over T1, so as my temperature increases, this means it had to be in a container that could change sizes because it says it's sealed, but it doesn't say that it's a fixed volume. And so it'll usually use the word rigid if the volume can't change. And so since it doesn't say rigid, we assume that this is an expandable container. And so as my temperature increased based on this relationship, my volume increased as well. And so if I consider my changes, volume's going to increase, temperature increases, moles does not change because it's a sealed container, and my pressure remains the same because it tells me that. So if my temperature is increasing, the last thing it says is particle speeds. If my temperature is increasing, then so is my particle speed, because my kinetic energy is equal to 1/2 mv squared. If my temperature increases, my velocity increases, which means my energy increases. Okay, so this is a continuation of the kinetic molecular theory video. My pen stopped working, so I had to stop the video and restart. And so in this problem, we have a container on the left that's holding carbon monoxide, a container on the right that is holding oxygen gas, and there's a closed valve in between them. It says determine the final pressure when the valve is left open for a long time in the apparatus represented in figure. Assume that the temperature is a fixed 300 Kelvin. Under the given conditions, assume no reaction of carbon monoxide or your oxygen. So in this problem, what we're going to have to do first, because it's wanting to know the final pressure, is we are going to have to figure out what the pressure is individually of carbon monoxide and oxygen before we can figure out what the total pressure is after we combine them. So we're going to be going back to this combined gas law. In the combined gas law, there's two sets of variables. The ones consider your initial conditions, the twos are your final conditions. And so depending on what the problem gives us, we don't use all of these variables. We don't always use pressure, volume, number of moles, and temperature. We can, but we don't have to. And so in this problem, all that's given to me is my pressure down on the bottom and my volume of each container. It tells me that my temperature is a fixed 300 Kelvin, so that means we don't care about it. And it doesn't tell us anything about the number of moles. And so we're not going to worry about it because they're the same number, because this is an enclosed system. So we're like what we saw a minute ago on this other example where it said in a sealed container, these are sealed containers, so gas cannot escape. So the moles would stay the same, so we don't need to incorporate them. So we're going to first solve for the carbon monoxide, and then we're going to solve for our oxygen, and then we're going to combine them to figure out what that final pressure is. So we're going to be using the equation, got to be on my pencil. We're going to be using the equation P1V1 is equal to P2V2, because we addressed on this last slide that we don't care about temperature because it's constant. We don't care about moles because it is equally constant because nothing is being added or removed. And so I'm going to do this for this side first. So carbon monoxide, my initial conditions for my pressure are 2.463 and 2 liters. My final conditions, we don't know the pressure, so that's what we're solving for, is the pressure of my CO. But my volume is now going to be both containers because it says the valve was left open. So this container is 2 liters, this container is 1 liter, so the container together is going to be 3 liters. Because gases can bounce around and they're going to spread out and reach an equilibrium where there's about the same amount of those gas particles in each container. So let's solve this out. So we're going to do 2.463 times 2 divided by 3. And that comes out to the pressure of my carbon monoxide is going to be, I'm going to do 4 sig figs based off of this pressure. Rounding to 1 sig fig gets really messy. AP would never expect you to do that. Okay, so now let's do the same thing for this one. So it is starting out at 4.926 atm. That time it is in 1 liter. I'm trying to find the pressure of my O2 in 3 liters. So again, I'm going to do the same thing. 4.926 times 1 divided by 3 is going to give me 1.642, which is the same pressure, because if you notice, this pressure is half of that, but this volume is double that. So mathematically, it ends up being the same pressure. But we need to know what the final pressure is. So we're actually going to be using Dalton's law of partial pressures. So I'm going to do my pressure total. So I'm going to add my pressure of my carbon monoxide plus my pressure of my oxygen. So 1.642 times 2, or plus 1.642. So my final pressure, my total pressure at the end, ends up being 3.284. So after I open up both of these and they're able to be left open and reach equilibrium, then final pressure is going to be 3.284. Again, AP loves molecule drawings, and so these are a few examples. So sometimes we have elements by themselves, and so if it's an element by itself, then it's just going to be a single dot hanging out. If they're gases, they're going to be spread out. If it is diatomic, such as any of the diatomic elements like hydrogen, oxygen, nitrogen, all those, then you're going to have 2 spheres connected. Again, they're going to be spread around if they are gases. If it is a compound, they use water a lot. Waters look like Mickey Mouses, and it's going to have your oxygen and then your 2 hydrogens. And so it sort of looks like Mickey Mouse head. And so you're going to have those spread out. Again, they are not going to be all in a fixed position. They're moved around and they're spread out and have space in between. My other example is ammonia gas. And it is, again, going to be spread out because they're all gases. So we get to this problem, and this problem is asking us, it says that we have this original 2-liter container, holds 1 mole of hydrogen gas at 300 Kelvin. It says add speed arrows on the ones that we need to show the motion. So a couple things about this picture initially. So the size of the box is my volume. Number of particles is sort of representing your moles. It's how much stuff is in that container. So this is giving us different conditions, okay? So this was 2 liters containing 1 mole of H2 at 300 Kelvin. It's asking me to draw another one with a 2-liter container holding 2 moles of H2. So I'm going to make a box that's roughly the same size. I'm never very good at this. And this one has 1, 2, 3, 4, 5, 6, 7. That means in here I need to have 14. I'm going to try to keep all of them about the same size. So mine are rubbing in together, but in essence, that's what you're going to end up with. AP usually gives you less moles if they ever expect you to draw another one, or this would be a multiple choice question and it'd already be drawn for you. Next one says, so these would be moving at the same speed as these because they are the same temperature. The next one says a 2-liter containing 1 mole of argon at 300 Kelvin. So we are going to use the basis of a mole as 1, 2, 3, 4, 5, 6, 7 particles. So I'm going to make another box, again, roughly the same size. Argon is not diatomic, so it is going to be larger than hydrogen, and there are only going to be 7 of them, but they shouldn't touch. And then my last one is 2 liters of container again. But this time it says H2 at 600 Kelvin. That means these are going to go much faster. So still 7 molecules. And let's say that up here it had arrows. Sometimes they'll have arrows. Let's say the arrow was about that long. Then that means that I would need to make these arrows roughly about twice as long. Now, none of these particles are going to have the exact same speed because the way that heat is absorbed is going to be different for each particle or molecule. And so they're not all going to have the exact same speed because of that equation. But it is going to go faster than the original one. So if AP was testing on your understanding of speed, then the higher temperature would have a longer speed arrow. So gases have really low density because they have a large amount of space in between them. They can be compressed so that we can squish them together because there's all that empty space, so it can squish and change the volume. There's two concepts that you're going to see that we see a lot of times in biology, but we don't talk about them as much in chemistry, is diffusion and effusion. So diffusion, a lot of times you'll see in biology when they're talking about materials moving through cells, but diffusion is the movement of one material through another. So for us, we're talking about gases. So it'd be like if somebody's cooking downstairs, let's say that you're asleep and your mom's cooking you breakfast and she's making bacon, and that's what wakes you up because the smell from the food has spread through the house and is in your bedroom. Or if I spray perfume up in the front of the room and then you smell it at the back of the room, that's diffusion. That just happens because particles that are gaseous just bounce around and move until they try to find that equilibrium where they spread out. Effusion is going to be the escape of a gas through a tiny opening. So if you've ever had a flat tire because of a screw or a nail in your tire, that was effusion. So the gas slowly escaped. You probably didn't pop the tire, but the air was escaping around that nail. So there are some questions that have to do with effusion. And effusion has a really weird equation. AP really is not going to ask you to solve for the rate of effusion, but I do want to show it to you with just one example at least. Effusion is going to be for the rates. You're going to take your mass of your second compound over the mass of your first compound and take the square root of it. And so if I was going to do this problem, I would say the rate of N2 over the rate of Ne is actually equal to the square root of the mass of Ne because it changes and it's on top. So sodium's mass is 20.18 over the mass of N2, which is 28.12. Whenever I work that out, it ends up being 0.849. And the unit for these is usually milliliters per minute. So just know that this is it's an example that exists. It is a math equation. It's called Graham's law of effusion. You can plug it in, solve it out, but AP is really not going to ask you to do that. What we really, really want to do is we want to make the connection that a lighter gas moves farther because it has a faster rate of effusion. So when we do these problems, you really want to, your questions are going to be worded differently than asking you to do this calculation. But this calculation does exist. In college level chemistry, sometimes they do have you solve these things. So this says a popular experiment involves the determination of the distances traveled by ammonia gas and hydrochloric acid gas from opposite ends of a glass tube. When the two gases meet, they form a visible white ring of ammonium chloride. Draw a line in the glass tube where you predict to see the white smoke form, which is meaning where are they going to meet to make that ammonium chloride. And so we have to figure out their masses because that's what it depends on. And so for my mass of my ammonia, it's going to be 17.034. My mass of hydrochloric acid is 36.458. This one is about twice as heavy as this one, which means it's going to move twice as slow. And so when you do these problems, you are trying to figure out where are they going to meet in here, which one's going to move faster and where are they going to meet. If they both have the same mass, they would meet here in the middle. They do not have the same mass. That means this one is going to move faster than that one. And so what's going to happen is roughly over in this region, this is where they are going to meet, and that is going to be where your NH4Cl is actually going to form, is over here, because this one moves so much faster. This one's really slow, so the particles are just going to have a really slow velocity, no kinetic energy compared to this one because they are so much bigger. So there's different ways that AP is going to ask you questions about that kinetic molecular theory. It just really is going to depend on if it's asking you to do one of these, because this really is an effusion question. It's just that they're not going to ask you to solve these calculations. Sometimes you're going to have to do these particle problems, and sometimes you're going to have to do some calculations using the combined gas law or just some explanations. So again, on this one, going back to it, sealed means that's your fixed moles, and rigid means fixed volume.